Time to go over the warm-up, so make sure you have your answer ready to check. So we have a formula here. So the first thing I need to do is plug in the volume of 36 pi. So we're going to go to R equals 3 times, instead of V, the 36 pi, dividing that by 4 pi, and they're going to raise that to the 1/3. Well, before I deal with the exponent, let's go ahead and take care of the inside the parentheses. First thing I notice is this pi and this pi can cancel. 3 times 36 is 108. So now I have that R equals 108 over 4 to the 1/3. Well, hopefully you check to see if 108 is divisible by 4, which it is, and you get R equals 27 to the 1/3. So now that exponent of 1/3 tells us that we need a radical house. With 27 inside. The 1 is on top, so it goes inside the house, but 27 to the first power doesn't change anything, so I'm going to ignore it. We put the 3 in the index, it wants to stay outside, and the cubed root of 27 is 3. That's one you should be getting pretty familiar with if you weren't already. Yesterday you were practicing, so you should have been checking your answer key. If not, make sure you come in and take care of that to make sure your answers were correct. Today we're talking about real numbers. Real numbers are any type of number that we've seen so far. In Algebra 2, you're going to see some kind of numbers we don't say are real, but that'll be next year, not this year. But we have different types of real numbers, and these you should have seen before, but if not, we'll be going over them today. So the first type is what we call a rational number, and that's any number that can be rewritten as a fraction or turn into a decimal. However, the decimal has to either terminate or repeat. If it's not rational, then we call it irrational. There are two separate categories, and an irrational number is a decimal that is non-repeating and non-terminating. It can also be some square roots, which they give you an example here. If you type in the square root of 3 in your calculator, you get a non-ending number. So your real numbers are composed of rational and irrational, and rational and irrational do not overlap. They are two separate categories. So we have this type of Venn diagram that shows our subsets. So the real number subsets or categories that you need to be familiar with are rational, integers, and whole numbers. And you also need to be familiar with irrational numbers. And they want us to classify -5, 0, the square root of the negative square root of 10, -8 over 17, 8, -12, and the cubed root of 2. And we have to put them in the Venn diagram that best fits them. So let's look at this. Rational numbers is any number that's inside this box, whether it's in this circle or not. It is also considered rational, because -3, if I wanted to, I could write that as a fraction by going -3 over 1. Same thing with 154. I could write it as 154 over 1. So whole numbers and integers are also called rational. Now, there are whole numbers that are also integers, but not every whole number is an integer as well. So to be an integer and not whole, it needs to fit into this circle. So anything here would not be a whole number. But any whole number is always considered an integer. So if it's a whole number, then we also, like 154, then it's also called an integer because it's also part of that circle. And it's also called a rational because it's also part of the box. So 154 has 3 subsets that it belongs to: whole, integer, and rational. And you have to list all of them in order to be correct. Listing only 1 or 2 of them is not a correct answer. So let's talk about -5. Well, -5 can be written as a fraction, -5/1, which means it's not going to go in the irrational category. So -5 is rational, but I have to decide if it's also another type of number set. Well, integers are positive and negative whole numbers. It can't be a fraction or a decimal for an integer. It has to be a whole number. Well, -5 fits that description, so we know it could go in this circle. Is -5 a whole number? Well, a whole number are numbers that you can count with on your finger that start with 0. So 0, 1, 2, 3, 4, and so on. Well, -5 doesn't fit that, so -5 goes in the integer circle, which means it is also a rational, but it is not whole. So go ahead and in pencil try to figure out where B, C, D, E, F, and G go, and then talk it over with your neighbors, see if you agree or disagree on any, and then unpause this when you're ready to check them. All right, B, 0 is a whole number, which means it's also an integer and it's a rational, because again, you could write it as a fraction, 0/1, and integers are positive and negative whole numbers. -(10), some people want to say because it's negative, it has to be an integer, but that's not the case. Integers have to be a whole number, and the square root of 10 is not. Square root of 10 would be a number that a decimal that doesn't repeat or end. So square root of -10 is an irrational number. D, -8/17. Again, don't be fooled by the negative. It's a fraction that can't be simplified, so it only goes into the rational numbers. 8 is a whole number. It's like the 0 and the 154, so it's also an integer and also a rational. -12, hopefully after that -5 you put that in the integer circle, which means it's an integer and a rational. And then G, the cubed root of 2. Well, since I don't know what the cubed root of 2 is, I know that that's going to go into the irrational category. And again, the diagram shows that all whole numbers are integers and all integers are rational numbers because the circles overlap. Continuing on, these are properties that you should have learned before this year. We've talked about a couple of them. Commutative and associative, there's addition and multiplication. Additive identity means you're adding by 0 because it doesn't change it. Additive inverse means that when you add two numbers, the result is 0, so you add opposites. The multiplicative identity is 1 because multiplying by 1 doesn't change a number. The multiplicative inverse is the reciprocal, because if you take a number and you multiply it by its reciprocal, the product is always 1. And the distributive property you're familiar with already. If you have two things inside the parentheses and you multiply them to the outside, you have to distribute that outside term to both. So these are just a little bit review of properties because we're going to use them to talk about closed sets. So we say that a set of numbers is closed under an operation if the result of that operation in any two numbers is also a number in that set. So they've asked us if -1, 0, and 1 is closed under addition. So that means every time you combine those three numbers by addition, you would need to get one of those three numbers because those are the only numbers in the set. So you start by adding the number with itself in its addition because it tells us. and then you go -1 plus -1, and then you would add the -1 with the next number, -1 plus 0, and then the next number, -1 plus 1. So we did all the negative ones, so then we switched to 0. Well, you take 0 and add it to itself, and then you add it to 1, and then you move to the next number, the 1. Well, you've already done -1 plus 1. You've already done 0 plus 1, so all you have left to do is 1 plus 1. Well, if you notice, when they did that, they got a -2 here and a +2. Well, neither one of these are located in the original set, which means this is not closed. B, show that the set of irrational numbers is not closed under addition. Well, if I add an integer or an irrational number with its opposite, I'm going to get 0. 0 is not irrational because 0 fits in the rational category, so that means it is not a closed set. So number 2 says to give an example that shows the set of integers, so think about what it means to be an integer, is not closed under division. So if you divide 2 integers, will it give you a number that you cannot label as an integer? So take a moment and see if you can come up with that, and then unpause it to see if it's one of the possible answers. And again, there's different possibilities here. All right, so any set of integers that would turn into a non-integer by division means it would turn into a fraction or a decimal. So for example, if I have 3 divided by 2, well, 3 is an integer, 2 is an integer, and if I divide those two numbers, I get 1.5, and since that's a decimal, that is not an integer. Now, you also could have done the same with the -3 and a -2. You would still get a number that is not an integer. Or maybe you took your number and you only made one of them negative. That is still not an integer because it's a decimal. So if you look at your example, if the two numbers turn into a decimal when you divide, then you're good to go. So now it says to give an example that shows the set of irrational numbers is not closed under multiplication. So you're trying to come up with an example when you multiply 2 irrational numbers that would turn into a rational number. So go ahead and see if you need to discuss it with a neighbor, see if you can come up with an example that would work for this. The easiest way to show that it's not closed would be to take 2 square roots that are irrational and multiply them. And the reason this works is the square root of 3 times the square root of 3 is the square root of 9. Well, what's the square root of 9? 3, and 3 is not irrational. That did turn into a rational number. So your square roots are pretty much what works. It's pretty much you're squaring an irrational number. Number 4, if you have whole numbers, which operations would the set be closed and which ones would it be not closed? Now when we talk about operations, we're talking about addition, subtraction, multiplication, and division. So try to figure out of those 4, which ones are closed and which ones are not closed. So whole numbers would be closed under addition. Because if I add 2 whole numbers, I'll always get a whole number. For example, 0 plus 1, 1 plus 5, 3 plus 2, all of those give me another whole number. It would also be closed under multiplication. One times 5 is another whole number, 2 times 10 is another whole number. So there's not 2 whole numbers when you multiply them that would turn into something else. Not closed fraction. For example, if I have 1 minus 5, that turns into a -4, and -4 is not a whole number. That starts off as an integer. It's also not closed under division because I could take two whole numbers, divide them, and get a decimal, which is not a whole number either. So it's closed under addition and multiplication, not closed under subtraction and division. So let's look at our two questions here. We're going to go ahead and do these together. We've got some other ones for you to practice on your own. So -2, 0, 2, closed under addition. So we start with -2, and first I add it to itself. And -2 plus -2 is -4. Well, is -4 one of the numbers in our list? It's not, so right away we know that this is not closed. And our explanation would be the fact that here's our proof, we got a number that was not part of that set. Now, could you have continued and added everything else together? Absolutely, but once you find one number that's not in the set, it's no longer closed. You also could have said it was not closed because 2 plus 2 would be 4, and 4 isn't a number either. Number 6 says to give an example that shows the set of irrational numbers is not closed under division. So we're looking for two irrational numbers that when I divide them, turns into a rational. Well, it's pretty much the same as when you multiply them. If I take an irrational number and divide it by itself, it turns into 1, which is no longer irrational. So any irrational number divided by itself would automatically give you a rational number. We're going to look through here through a proof. We haven't really seen these before, so they're a little bit hard to walk through, so we're going to do it together. So the first thing it says is we're going to begin with the definition of rational numbers a and b. So our first step is a and b are rational numbers, and they tell us that. Well, if it's a rational, that means it can be a fraction. So we say a is the same thing as p divided by q, a fraction, and b is the same as r divided by s. And that only works if the four numbers here are integers, and the denominators cannot be 0. So we're talking about being closed under addition. So if I add my original numbers a plus b, that's the same thing as adding their fraction equivalents, pq plus r over s. Well, in order to add fractions, they have to have a common denominator. So the q here needs to have an s, and the s needs to have a q in order for them to be common. But I can't just change the bottom, I also have to change the top. So the first fraction, I need to introduce an s, so I get ps on top and qs on the bottom. The second fraction needs a q, so I have rq, or qr preferably, to be honest, and I'm going to write it as qs on the bottom instead of sq. Well, now that the denominators are the same, I can add the numerators. So I end up with ps plus, I'm going to switch it to qr, and again that's all over qs. And again, proofs are a little bit hard. We haven't seen them yet. They're more in geometry, but we need to start familiar with how they look. So we're going to keep on going with this proof. And here's our conclusion. Because the numerator pq plus qr and the denominator qs are both integers, and we know they're integers because on the other page it had told us that those 4 letters are all integers. Well, if I take 2 integers and I divide them, I'm going to end up with a rational number. Again, very different type of style than what we're used to, which is why we worked through that one together. So now we have to figure out of our main number sets, real, irrational, rational, and integers, which operations they're closed under. So go ahead and take a moment to say yes or no to these. Do this in pencil so you can erase if needed, but hopefully you won't have to. Check your tables with a neighbor, and then unpause this when you're ready to see if you answered them correctly. All right, well, real numbers, that's pretty easy. It is closed under all sets because there's no way to take 2 real numbers and get a non-real number. And again, you'll talk more about those in Algebra 2. Now, irrational, we already talked about the fact that it is not closed under division or multiplication. If I add 2 irrationals, I would still get an irrational number. And if I subtract them, it is not closed. Check that one carefully. And the reason that one is not closed is because if I subtract, for example, the square root of 3 minus the square root of 3, I get 0. And 0 is not considered irrational. It is considered rational. So now let's talk about rational numbers. If I add 2 rational numbers, there's no way I'm going to get an irrational number, so it is closed. If I subtract them, same thing, I'm not going to get an irrational. I could get 0, but 0 is rational, so that's okay. If I multiply 2 rational numbers, I would end up still with a rational number. And if I divide 2 rational numbers, I would still get a rational number. It wouldn't turn irrational. Now, integers, we already said that if you divide 2 integers, you could get a decimal, so it's not closed under that. If I add 2 integers, so like -5 plus -5, or -5 plus 0, those are all still going to be integers, positive and negative whole numbers. If I subtract 2 integers, it's not going to turn into a decimal, so that's going to be a yes. And if I multiply 2 integers, multiplying 2 integers will not turn it into a decimal or a fraction either, so it is also closed under multiplication. And again, the biggest thing to remember is a whole number is also considered integer, positive and negative whole numbers. You're going to jump to page 42, so I'm going to give you a second to turn there, and we're going to do a few problems. You're going to try a few problems, and we'll go over them to see how you're doing. So go ahead, and I want you to try to do numbers 1, 2, and 3, and then unpause the video when you are ready to check those 3 answers. All right, so number 1, they give us 2 numbers in the set. So we start by going 0 times itself, which is 0. That's a number in the set, so far so good. Then we go 0 times 1, which is 0, still a number in the set. And then we move to the next number, 1. Well, I already multiplied the 1 and the 0, so now I go 1 times 1, which is 1. That's still part of our set here. So that means this one is closed. Okay, we have that same set, but now with addition. So I first start by going 0 plus itself, which is 0. Then I go 0 plus 1, which is 1. But then when I move to that 1 and I add it to itself, I get 2. 2 is not part of that number set, so it is not closed under addition. And then even integers. under addition, would you always get another even one? So even numbers, we're talking about 0, 2, 4, 6, 8. So you could even take a couple examples. So let's go 2 plus 0. Well, that's 2. That's still an even integer. Okay, well, what if I take two positives and add them together? That still gives me another even integer. Well, what if I take a positive even integer and a negative even integer? Well, in this case, that's 0. That's still an even integer. Well, what if I have two negatives? Well, that's still an even number, so this one is closed. So now let's look at one more proof, proving that the set of rational numbers is closed under multiplication. So the first thing is a and b are rational, which means we can write them as a fraction. And we're talking about multiplying, so we're going to go p over q times r over s. Well, p times r is pr. Q times s is qs. I know that these are integers because integers are closed under multiplication. So pr and qs would be an integer. Well, if I divide them, I know that that turns into a rational number because it could turn into a decimal, which means it is closed under multiplication because we wanted it to be rational numbers closed under multiplication.